Hi, my name is Philipp Schaad. I'm with the Scalable Parallel Computing Laboratory at ETH Zurich, and I would like to demonstrate how we can use interactive data movement visualizations to boost performance optimization workflows. So over the past couple of decades, we've been able to rely on a fairly steady improvement in the efficiency and performance of our computational hardware. However, a cost that has remained fairly constant over the years is the cost of actually moving individual data bytes from memory where they reside to the site of the actual computation. And so indeed, if we look at the trend in recent decades, what this means is that to perform computations, the cost of moving the operands even just 5 millimeters on the chip or even from memory to the site of the computation now drastically outweighs the cost of performing the computation itself. And so to optimize applications nowadays, this means that we have to reduce this data movement as much as possible, consequently exploiting both spatial and temporal data locality as much as we can. To optimize an application for this reduction in data movement is relatively complex though. The factors that can govern an application's data access and reuse behavior are very interlinked, and so before you're able to perform such optimizations, you usually have to perform a very detailed performance analysis before that. But moreover than that, because these factors are so interlinked, even minute changes to the application, such as through the optimizations themselves, can actually have a very drastic effect on the data access and reuse behavior. And so before you're able to perform additional optimizations, you usually have to reanalyze the performance of the application. And so this means that this data movement optimization workflow is a very iterative process with analysis and optimization phases following one after the other repeatedly until you're satisfied with the performance. Now, to perform the analysis, there are a variety of tools available that can help the performance engineer with that. These are, for example, performance counters or profiling tools that try to gather as much data about the application's behavior as possible, allowing you to make informed decisions about optimizations. But the problem is that these tools generate a wealth of data, and sifting through this large amount of data for the performance engineer can be relatively difficult, and it might be hard to actually extract any meaningful insights from that amount of data. Now, this is where performance visualizations come in, where the idea is that they take this data and aggregate it and present it in a much more interpretable manner, and hopefully already expose some potential performance issues to the performance engineer. But the problem is, even though they actually visualize the data very nicely, they still have to execute the program itself to gather the data that they use to visualize. And if you have a large application, this execution can take a long time. Now, because the data movement optimization workflow is an iterative process, you're potentially introducing this dead time many times before you're able to perform optimizations. And so this makes this entire process very non-interactive. Now, to fix this, we propose an analysis approach where you don't have to execute the program before you're able to gather insightful results about the data access reuse behavior of the application. And the way we do this is by providing a performance visualization geared towards data movement reduction integrated into the IDE Visual Studio code, where the main idea is that we can gather and visualize performance data without requiring the program execution, and instead by gathering it through static data flow analysis and through small-scale parametric simulations. Now, to facilitate this, we don't actually analyze the program source code directly, but rather we translate a program into a Dataflow intermediate representation that allows us to do these analyses. The Dataflow IR can then be used to perform optimizations on the program, and then an optimized version of the Dataflow IR can be turned back into either highly optimized program source code or a highly optimized program binary. Now, to do this, or to allow us to pursue this workflow, we use an existing framework called the DACE framework, which has an integrated Dataflow IR called Stateful Dataflow Multigraphs, or SDFGs for short. And the reason we use this is because DACE actually has a way of generating such Dataflow IR graphs from a variety of different front-end high-level languages such as Python, C, and Fortran. It additionally has ways of then performing optimizations on this Dataflow IR and can turn this optimized Dataflow IR into generated code for a variety of target architectures, including FPGAs and GPUs. And so DACE already covers a large portion of this entire workflow, helping the performance engineer with individual steps. And this allows us to focus in this work solely on the performance analysis aspect. Now, before we're able to see how we can analyze this Dataflow IR, let's actually look at how it is constructed. So we can do this by looking at a simple example. We have a vector outer product here between two vectors A and B, and we have a very simple Python implementation of this. Now, if this is fed through DACE, this generates this stateful Dataflow multigraph intermediate representation from this program. And as the name multigraph might imply, this is a graph-based intermediate representation. And so if we look at a screenshot from our tool, this is the SDFG that is being generated from this program. And the idea in this SDFG is that the graph nodes actually represent data containers, such as the vectors A and B or the matrix C, and they represent the computations, such as the multiplication in our case here. And then the directed edges that you can see that connect these data containers and computations actually represent data movement through the program. So they represent data moving from data containers to computations or from computations to data containers, etc. Now, entire such computation subregions or entire subgraphs can be nested inside of these two trapezoidal nodes that you see here that represent parallel regions or parametric parallelism, where the idea is that the entire contents of that parallel region are mapped onto a set of parameters. So in this case, the parameters I and j, and this represents the nested for loops that we have in the original source application. And then finally, entire such program graphs are actually put inside these blue containers called states, where the idea is that by using states and a series of state transitions, this allows SDFGs to express complex control flow or even data-dependent execution. So now that we have an SDFG program, let's look at how we can analyze this. Now, the directed edges in the Dataflow graph already natively expose where data is flowing. But we're not only interested in where data is flowing, we're also interested in how much data is flowing or the data movement volume. And so to analyze this, we can actually leverage a property of SDFGs, which is that each data movement edge is annotated with the exact data subset that is being accessed or moved across that data movement edge. And so what we can do to analyze this data movement volume is actually look at computations, and for each of the edges connected to the computations, we can use the movement subset that is annotated there to derive the exact volume of data that is being moved across that edge. And we can now propagate this through the rest of the graph. So by knowing that this computation is executed a total of n by m times, we know that the resulting volumes outside connected to the data movement edges inside the parallel region move a total of n by m elements across them. Now, not only can we derive the data movement volume statically, we can also look at the number of arithmetic operations statically. And so we can proceed in a very similar manner, looking at the computations, and by parsing the abstract syntax tree inside of the computational nodes, we can derive the number of arithmetic operations for each computational node. And now we can propagate this information through the rest of the graph again by knowing that the computation here is executed a total of n by m times. The entire parallel region contains a total of n by m arithmetic operations. And now finally, we can combine these two metrics to derive an operational intensity. And we can do this for each of the graph nodes in our program graph, combining the arithmetic operations count with the data movement volume to get for each graph node the operational intensity. Okay, so now we have formulas that express the data movement volume and the arithmetic intensity as a function of the input parameters and an m to our application here. So what we can do now is we can plug in values for the input parameters, such as the ones that we might expect to see in practice, and we can substitute these in to give us concrete observations for the data movement volume and arithmetic intensity given a set of input parameters. Now, by expressing the data movement volume as a function of the input parameters, this actually allows us to perform a very powerful scaling analysis. So by changing an input parameter, we can on the fly recompute the data movement volume that we expect to see. And this gives us new observations, allowing you to observe how the data movement behavior of the application changes with respect to changes in the input parameters. This is something that usually would require a very expensive recomputation or re-execution of the application to gather new performance data with different input parameters. Okay, so now this is great and it gives us actual observations for the amount of data movement and the operational intensity in our program. But it can be very difficult to analyze this for a larger application. If you imagine you have a large program graph and all you have are these numbers annotated to the data movement edges. So what we can do now is we can visualize this information. And we do this by using a heat map technique, where the idea is that we color the data movement edges on a color spectrum ranging from green to red. And the more data a data movement edge moves, the more it leans towards the red end of the spectrum, and the less data it moves, the more it leans towards the green end of the spectrum. And what this allows you to do is, even for a large application, you can spot at a glance where you might have a data movement bottleneck by spotting some red colored regions in the program. And of course, the same technique can be used not only to visualize the data movement, but also to visualize the number of arithmetic operations or the operational intensity. Of course, instead of coloring the data movement edges, coloring the nodes instead. Now, as I mentioned before, this SDFG representation, or DACE, actually allows you to perform optimizations on the SDFGs directly. Now, traditionally in optimization workflows, you would have to switch between the analysis tool and your source code representation where you perform the actual optimizations. However, because we can optimize the SDFG representation directly, we are actually visualizing the performance data in situ directly on top of the program that you're optimizing. And so this drastically reduces the amount of context switching you have to do between different program contexts, in turn drastically reducing the cognitive overhead that might be introduced through such a process. So now let's look at what this looks like in practice. So we can analyze the encoder layer of a BERT transformer. That's a natural language model. And if we take a naive Python implementation and feed it through DACE, this is the SDFG that is being generated. Now, by using the data movement overlay, we can immediately see that there are two regions here where there's a lot of red colored edges, which might be indicating a high volume of data movement and consequently a potential data movement bottleneck. Now, if we take a closer look at these two program regions, it actually turns out that these are parallel regions with very similar parallel bounds or loop bounds. And so what this means is that we can actually employ a traditional loop fusion optimization, fusing these parallel regions together, which drastically reduces the amount of data movement that we have and consequently might improve the behavior or the performance of our application. Now we can go further than that, and instead of using the data movement overlay, we can look at the operational intensity heat map. And again, what we can see is that there's two regions here where there's a lot of green colored nodes. Now, green colored nodes in the terms of operational intensity means a low operational intensity. So for the amount of data that is being used, we're not potentially using the data as efficiently for computations. And by taking a closer look at these two regions, again, this uncovers that these are, again, parallel regions with very similar bounds, meaning that we can fuse them together. And as you can see by the color change in the resulting parallel region, this has a much higher overall operational intensity, and so consequently makes much better use of the data movement. And indeed, if we now benchmark the application, the optimized version, and compare it back to the original version of the application, we can see that this gives us a 30.2 times speed up over the original implementation. And we are able to obtain this speed up by using analysis results that we obtained essentially within milliseconds without having to wait for program execution. Now, this is already great, and it allows you to optimize the sort of global data movement behavior of your application quite significantly. But in many cases, this just isn't enough, and you actually have to perform optimizations on a much finer scale, essentially optimizing the fine-grained data reuse and caching behavior of your application. And this is where you have to perform a much more close-up data reuse analysis. This is something where you traditionally would use performance counters to measure metrics such as the number of cache misses or the number of load store operations that your application actually incurs. But we're trying to avoid that. So what can we do instead? Now, what we can do is we can simulate the data reuse behavior. But an issue with simulating the data reuse behavior, especially for a large application, is that this might take a long time. And actually, it might take longer than just executing the program and using something like performance counters. But what we can do is we can leverage this graph-based intermediate representation. And by using something like the analysis overlays that we've seen before, this allows the performance engineers to drill down onto a section of the program they're actually interested in analyzing more closely. And then we can specify this region and cut it out of the original program and simulate only that part of the program in isolation. But simulating that small part of the program with the original input parameters or input data might again be relatively expensive because the program might be operating on a very large amount of data. And so what we can do instead, we want the simulation to essentially only take a couple of milliseconds to give you a very fast feedback on the performance. And so what we do is we specify small example values for the input parameters that we might be expecting to see in practice, such as in our case here for the parameters n and m, we provide small values 3 and 4. Now, how we can choose these values and how well this generalizes to the actual full-scale setting is something that we will see in a little bit. But let's first look at what we can do with this now that we have parameterized the value or the input parameters with such small values. So this actually allows us to parameterize the entire application. And so instead of drawing the data containers, for example, as these abstract blobs that we have on the left side, what we can do instead is we can draw them in their full size. So we now know that A is a vector of size 3, and so we can draw for each data element in the vector, we can draw a separate little square representing that data element. And so this shows A, B, and C in their true size. But not only can we parameterize the data containers, we can apply the same technique to parameterize the parallel regions. Because we have parameterized the input parameters, we now know the exact intervals or bounds for each of the parameters to the parallel region. And so what this allows us to do is we can render for each of the parameters a slider that allows the user to select a specific value inside of the bound for that parameter. And so we can substitute this in to the axes for each individual loop iteration. And this allows us to visualize for each loop iteration what exact data elements are being accessed by that loop iteration. And so this allows the user in turn to play with these sliders and get an idea for how or what data elements are being accessed by an individual loop iteration of their parallel region. Now, a problem you might spot is that this works very well for 1- and 2-dimensional data containers, but it might become a little bit more tricky to visualize this if you have something higher dimensional, something like a 3-dimensional data container or even higher. So to see what we can do to visualize this, let's look at an example where we have the 4-dimensional weights of a convolution. And the way we handle this is actually by first taking the 2 innermost dimensions and just visualizing this as a traditional 2-dimensional grid. Now I can take the next dimension and take everything that we have so far, replicate it horizontally by as many times as that dimension specifies. We can then proceed similarly, taking again everything we have so far, looking at the next dimension and replicating everything vertically by as many times as the dimension specifies. We can proceed in this manner if we have more dimension and just alternate between replicating horizontally or vertically to save on space, essentially flattening the entire data container and showing all dimensions crucially at the same time. So putting this together, we have a parameterized version of a convolution operation here, both with the data containers and the parallel region parameterized. And so what this allows us to do now, we know for each iteration of the parallel region exactly what data elements are being accessed, and we know the exact loop bounds for the entire parallel region. And so what we can do is we can simulate the iteration space for that loop region and essentially simulate the entire access pattern. We can use a visualization then or an animation to play this back to the user, showing you what data elements are being accessed in what order and how many times. Now this time dimension, of course, can be flattened, and we can show instead a heat map that shows over the entire course of the application what data elements are being accessed how many times and the distribution of the number of accesses. Now, we don't have to play back this access pattern, but we can instead turn it on its head and say, for any given output elements, what input elements are being required to perform the computation for that output element. And so if we look at a matrix-matrix multiplication here, if we select an entire column of the output matrix C, this shows us that the entirety of the matrix A is being accessed exactly once, whereas an entire column for the matrix B is accessed repeatedly. And so what this allows us to do is make some informed decisions about tiling or explicit caching strategies. Now, knowing the access pattern is part of the story to analyze spatial locality, but the other thing we need is to know how the data is actually laid out in memory. And we can derive this information by looking at the element size for each of the data container, and then combining this with the size of a cache line and the strides given for each data container. And what this allows us to do is, if the user specifies a given data element, we can derive the exact other data elements that belong to the same cache line and will be pulled into cache alongside that element, and we can visualize this. And in doing so, we essentially expose the physical data layout for the data container. So this shows us that in this case here, the data containers A and B are stored in a row major format, whereas the data container B is actually stored in a column major format. And so this, in combination with the access pattern exposed previously, gives the performance engineer an idea of how well we're exploiting spatial locality. But spatial locality is only part of the picture to data locality. The other side of the picture is temporal data locality. And so to get an idea of how efficiently we're using temporal locality, we have to get a metric with which we can measure temporal locality. And for that, we use the stack distance at a cache line granularity. What that is the number of accesses to unique cache lines since the last reference to any given cache line. And now, because we know the exact access pattern, and for each of the accesses we know the associated cache line, we can essentially go through our access pattern and sum up the stack distances for each of the accesses that we have. And now we can use a heat map to visualize this, essentially showing for each data element in our data containers the median stack distance for all the accesses to that data element. And in addition to this, we can, of course, give a detailed breakdown. By selecting a data element, we can show a histogram that shows you, for all of the axes to that data element, the distribution of stack distances across those axes. And now that we have a metric to measure the temporal locality, we can see how efficiently we're using it by counting the number of cache misses that we would incur given this axis pattern. Now, the first thing we have to count are cold misses, and this is simply any axis where the stack distance is infinity, meaning that the cache line for that axis has not been accessed previously. The second thing are capacity misses. This is counted whenever we have an axis with a stack distance that is greater than or equal to some stack distance threshold TD, assuming a last recently used policy, of course. And the reason we use a variable stack distance threshold TD rather than the fixed cache size is because this allows us to actually model different cache sizes for different architectures within sort of the same modeling environment. Now, finally, we would have to count conflict misses, but we can actually avoid having to do this by assuming a fully associative cache. And the reason we can do this is because previous research has shown that the majority of cache misses is actually due to capacity and cold misses and not due to conflict misses. And then subsequent research was able to show that modelings and simulations done on fully associative caches generalize really well to low set associative or even direct mapped caches. And so by setting a stack distance threshold TD, in this case, for example, 4, this allows us to, going over our axis pattern, count up the number of stacked cache misses that we would incur, and then visualize this again with a heat map for each of the data elements, showing the number of cache misses to that, with accesses to that data element. And by changing the threshold, you can see that this immediately has an effect on the number of cache misses that we count, essentially giving us the option to model a different sized cache. And now finally, we can use this information to actually combine it with the size of an individual cache line, and that allows us to determine exactly how much data is being moved due to the number of cache misses that we get with our axis pattern. Now, putting this all together, let's look at what this looks like in practice. We're optimizing or analyzing here the performance of a stencil operation, specifically a horizontal diffusion stencil, which is a fundamental operation in weather and climate simulation. And we have parameterized this operation here with the parameters I and j equals to 8 and k equals to 5. Now, how do we arrive at these parameters? Well, we found that a good strategy for determining the toy parameters to use in the simulation is actually to look at the full-sized settings and the parameters that you would expect in that case. So in this case, we're expecting to see for I and j sizes 256 and for k 160. And the good strategy then is to determine a common scaling factor to apply to each of these parameters to get them down to a range of somewhere between 1 and 20, which makes them small enough to get very fast simulation times within a couple of milliseconds. And so in this case, we use a scaling factor of 32 that scales the parameters down to the values that we see here. And now if we use the cache line overlay, we can see that this actually shows us the data layout in memory, giving us that k in the input container here is the contiguous dimension in memory. Now, if we use the sliders in our parallel region to visualize the axis pattern for each loop iteration, we can actually see that each loop iteration accesses data that is spread across a non-contiguous dimension. So this makes very poor use of spatial locality. A way to fix this is to actually reshape the data container. So if we look at the cache line now, after reshaping, the j+4 dimension is actually the contiguous dimension in the data container. And so if we look at the axis pattern for a single loop iteration, we see that this now makes much better use of spatial locality with all the axes being much closer together in memory. Now again, we can use the sliders to essentially play back the loop iterations. And while each individual loop iteration, as shown here with the axis pattern, is now accessing data closer together and making better use of spatial locality, we're now jumping in loop iterations across a non-contiguous dimension. So we're making very poor use of the cache, essentially polluting the cache in previous loop iterations and then not using what we have pulled into the cache. Now, a way to fix this in this case is to actually reorder the loops that we have. So instead of going over I, j, and then k, we now reorder it to make k the outermost dimension. And if we use the animation to play back the axis pattern, we can see that now indeed we actually make much better use of the cache, accessing data across a contiguous dimension and iterating over a contiguous dimension. And if we look at it before and after, using the overlays showing the number of cache misses and the amount of physical data movement, we can see that indeed in the unoptimized version on the left side, we have a much larger amount or higher amount of cache misses and a much larger amount of data movement. And with the optimizations, this simulation predicts about a 10.3 times reduction in the amount of data movement. If we now benchmark the application or the optimized version, we can see that indeed we get a 138 times speed up. And if we use hardware counters or performance counters to measure the number of cache misses, we can see that indeed we actually get a 9.6 times reduction in the number of cache misses and consequently the amount of data movement, which is very close to the predicted value, even though we simulated with much smaller data sizes. So in conclusion, what have we seen? What can we do now? So this allows us to actually optimize and analyze the global data movement behavior of an application and the fine-grained data reuse and access behavior of the application, essentially within milliseconds without having to wait for program execution. And this allows us to perform analyses and optimizations essentially with the click of a button. Now, where can we go next with this? While we have focused here on manual optimizations through analyses from a user, what this essentially exposes is metrics that are usually only available at runtime. And so we're exposing these statically, allowing a compiler or an automatic optimizer to potentially perform much more in-depth optimizations with much greater levels of insight on the application's behavior. In addition to that, we're using a very crude cache model here. This could potentially be extended with a much more detailed hardware model, modeling different levels of caches, which gives you a much more detailed insight into the performance behavior of the application. Finally, we would stipulate that this tool has a very high educational value, essentially exposing for complex applications their data access behavior and patterns in a very trivial manner. So as I mentioned, all of this is implemented in a Visual Studio Code extension. This is, of course, freely available on the Visual Studio Code Marketplace, so feel free to try this out for yourself and play around with it. The source code is also open source and freely available on GitHub. We welcome any comments that you might have and any feedback that you might have, as well as any contributions. And with that, I would like to thank you very much for your attention.